As an interesting new feature of the first virtual Ifac World Congress, all plenaries and semi-plenaries are accompanied by a live element. This presentation is followed by a live panel discussion where experts in the field recapitulate and debate on related ideas, questions, and open problems.
Welcome to this first live plenary panel of the Ifac 2020 World Congress, where we will try to shed light on different questions, developments, and perspectives related to the interface between machine learning and control. My name is Frank Allgöwer from the University of Stuttgart in Germany, and I will be the moderator of this panel session. Let me first introduce our first four distinguished panelists. Melanie Zeilinger is an assistant professor at ETH Zurich, Switzerland, where she is leading the Intelligent Control Systems group at the Institute for Dynamic Systems and Control. Melanie and her group develop learning-based intelligent control solutions for safety-critical systems that integrate control, learning, and optimization. For her innovative research, she already won a large number of awards and recognitions. The second panelist is Thomas Schön, who is the Bayer Professor of Artificial Intelligence in the Department of Information Technology at Uppsala University in Sweden. He has a broad interest in developing new algorithms and mathematical models capable of learning and acting based on data. He has been elected to 2 Swedish Royal Academies. Carson Scherer is a professor for mathematical systems theory at the Department of Mathematics at the University of Stuttgart in Germany. Carson strives for developing unifying methodologies for designing structured feedback controllers that are resilient to uncertainties. He is recognized as an IEEE Fellow for his contribution to optimization-based robust controller synthesis based on LMIs. Finally, Mario Snyder is the Dennis Picard Trustee Professor at the ECE Department, Northeastern University, USA. Lately, he has been interested in problems at the interface of robust control, machine learning, and sparse optimization, and in particular on the problem of extracting control-relevant information from large data streams. He is a distinguished member of the IEEE Control Systems Society and an IEEE Fellow in recognition to his contributions to robust control, identification of hybrid systems, and dynamic visions. As you heard, we have 2 panelists who are with us actively embracing the possibilities of the new machine learning age, Thomas and Melanie in particular, and 2 open-minded experts who are deeper positioned in the classical model-based control world, Mario and Carson. That mix promises to lead to interesting discussions. Let's kick this exchange off with a question to Mario. Mario, in recognition of your services to this panel, the Congress organizers are willing to buy you a first-class ticket to the Caribbean in Lufthansa's inaugural self-piloting flight. So, no pilot on board. Will you take it?
Wow. Thanks, Frank. That's really generous of Ifac. Of course I will take it. I mean, I want to see Lufthansa's first-class terminal in Frankfurt. Maybe they will even drive me to the airplane on a self-driving Porsche. I just have a small request for Ifac. I think you can do it. Can you just make sure that there are no other airplanes in the flight path and that the weather en route is going to be exactly like you trained? Then, of course, I will go. Okay? So honestly, I think that long ago we learned that control is all about managing uncertainty. And we came up with this revolutionary idea that we call feedback that gives you a way of making yourself insensitive to things that you don't know. And not only that, you get certificates that things are going to work. Okay? And even though machine learning has made amazing progress in the past decade, I don't think we're right there. Because firstly, I don't think we can get certificates of the type of thing or certificates we get in control. And maybe Melanie can correct me if I'm wrong. But more importantly, what happens is that many times you have to learn from a single execution. You're flying your airplane and a sensor goes bad, and no one actually trained for that because no one ever thought that that's going to happen. And then you're in trouble. I'm optimistic because humans can do that. If you actually Google B-59 landing without tailplane, you're going to find in YouTube an amazing video of a pilot flying an unflyable airplane and doing it. And obviously no one trains for an airplane with a missing tail. I don't think we're there yet. So I think the regulator, I would have to take a rain check until you can arrange for the weathering route.
So thanks, Mario. That saves us a lot of money, potentially, at least. And but you asked Melanie, right? Melanie, maybe you have a different perspective on that. Maybe you're not such a chicken as Mario.
Yeah, thank you. That's a tough question, Mario and Frank. But if you think about it, as you also pointed out, I mean, there's a lot of things are already done by the autopilot. And so for the regular events, it's no issue at all. And actually, I think there's another important point to take into account. And this is that often there is an issue because of that interplay between the pilot and the autopilot. And actually, this exchange of information that's missing there is where things often go wrong. There's now been a lot of analysis on that. So this is good motivation to think that maybe, you know, having the pilot there can actually have a contrary effect, and it would be better to think about an airplane that's just self-piloting. However, now you're absolutely right. In the uneventful flight, no problem. What happens in all of these difficult situations where things do go wrong? Well, this is exactly where learning can help us, where we need to learn and figure out these sort of new actions from the information that we're currently seeing. But regarding sensors, I do think you know, this is a big issue, and the redundancies that would have to be there for me to go on this flight for the moment. I think I would also still be slightly on the chicken side and not enter without the backup pilot on board. But maybe, you know, maybe the others can talk a little bit more about what we can do to make this trustworthy.
Okay, thanks, Melanie, very much. But now comes the idea, Carsten. Let's use robust control technology to protect against those potential misclassification things that can go wrong. How about that? Can you say something about that?
I'd say I'd be a fool if I said no, right? So, I mean, of course, I believe in robust control techniques, and I think there is a huge potential to marry those learning issues with robust control. And it's already there. I mean, people do it. It's active research. I mean, in Melanie's work, we see that. You know, there is a revival of dual control in model predictive control for safety guarantees, and other techniques like robustness techniques emerge in analyzing neural networks, for example, you know, bounding proper the Lipschitz constant of such neural networks, for example. That can be done by robust control techniques. So you see these things emerging. I mean, after all, these are neural networks are Lurie systems, and this is a classical thing to consider. However, as Melanie pointed out, and if you think of human in the loop, or if you think of like uncertain environments in autonomous driving, you know, then new types of uncertainties come into the picture, and we are not really. Sorry, I heard a voice now, sorry. We are not really sure how to handle these new types of uncertainties that emerge in machine learning. So, I'm sorry, I hear some voice here. Okay.
Try ignoring it, Carsten.
Okay, sorry. So the question is, how can we handle those things? How can we handle these uncertainties in robust control? We need a robustified learning, I think, and bring then in this fashion robust control and robust learning furthermore together. And it's really important, I think, to learn next to models, really the uncertainties, to do a combination thereof, and to understand much better for such complex types of uncertainties, how to adapt controllers, which this adaptation should go beyond parametric adaptations and parametric uncertainties, of course. So I really envision techniques that permit to get to analyze the trade-off for safety and performance in an online context, very much like the things that we have seen in classical robust control, like frequency domain techniques. And honestly, I also want to make a point in proposing actually technically that Williams distributivity theory is still a good common ground for addressing those questions, both on the theoretical side, I think, and on the computational side, both for analysis and for synthesis, because it's trajectory oriented and it combines its trajectory orientation with certificates for stability, for performance, those things that we really do like. And stochastic distributivity, for example, could be a way to go to bring the worlds of robust control and reinforcement learning closer together. So I'm sure, Maria and Melanie might have more trust if they know that these techniques are really applied in the background.
Okay, so we know those techniques might be there, right? But I nevertheless hear a certain agreement that we better save the money and not give it to Mario for his first class flight. So Thomas, you are active both in machine learning and control. If we give the money instead to you for your research, when you will be able to deliver a solution that Mario will trust?
Yeah, that's a good question. So I think there's still a fair bit to do, obviously, but at the same time, there's lots of interesting work in this direction that has been mentioned already. And I think actually picking up on what Carsten said here, so to me, the key takeaway lesson in contemporary machine learning is the following one. It's that flexible models gives us the best predictive solutions at the moment. So if that is true, then the next question would be, so what's a flexible model? Well, one example is deep learning, obviously, which is a highly flexible model. Another one is Gaussian processes. So these flexible models are currently not really playing along with our more classical tools from control. But that doesn't mean it's not possible. It's certainly possible. And that's something that we're looking at and several others, where if you can merge the robust control IDs with these flexible predictors, you get a much better way of dealing with the unknown uncertainties, if we call them that will emerge in such an endeavor. And then you have the exploitation trade-off to actually actively plan how to get informative data where I see that there is lots to be done. So that's also an active area. And then as Mario mentioned, these certificates, well, that sort of goes together with the robust control, I guess, merging that with these flexible models. But I would also like to stress something I've learned myself. I mean, we talk about, me includingly, the technologies here. But the idea, one of the key things with moving in between communities is really culture and human beings. So that to me has given a lot of energy and gives you new insights. So traveling between different cultures and communities, I think, is extremely important for science, just as important as the technical ideas that we talk about. So that's a strong encouragement to especially to younger people to actually go to new fields.
Okay, thanks, Thomas. Now, Carsten, this was a statement that Thomas has ideas how to move forward. Are you convinced? Are you willing to chip money in and instead of flying first class, finance Thomas' research?
Oh, I think one should invest in both worlds. I mean, there is no doubt about that. So I really take the comment of Thomas. I fully agree that at the interface, that's really interesting things are happening. For example, from the perspective of systems and control, new techniques come into play. I mean, like kernel methods, probabilistic methods, reproducing kernel Hilbert spaces and all kind of things. Gaussian processes, we heard about those. And yes, these techniques are already applied in systems and control. In MPC, we see that, right? To model mismatches between known and unknown parts of your systems. But this concerns also the full description of models. So I want to make a point over here, actually also a little bit motivated from classical robust control, that, you often see what's called unstructured uncertainties, to model those mismatches. And, this is often rather conservative. So I really think it's instrumental to to really take much more into account the prior information in models. You then capture residuals that you've got in a much more structured fashion. So I've been collaborating a lot with Philips in industries, with ASML. So that's the world's biggest manufacturer of wafer scanners, these complex mechatronic machines. And if you talk to those people over there, they would never give up on using their models that they trust in, that they have available. But they would, I'm sure they would love to model those components of their system by direct database techniques that they cannot handle otherwise. Yeah, so I see this mixture really as an important step forward. And of course, this should come along with error bounds in order to get to the guarantees that we already discussed. So in my imagination, it's really such a structured learning of uncertain components, offline or online, that requires novel combinations of machine learning and robust control. And at least for those people in the high-tech industries that I'm talking to, this is really an enabler, and they, well, might even invest money in that. So I think at the interface is really where things should be done more research on.
So talking about industry, let's try looking into the crystal ball, Melanie. Do you see learning control to replace, say, PID in industrial applications? And if so, when do you think this is replaced?
In a sense, I'm afraid it will be. No, but more seriously, I think what we're seeing is a little bit of a pressure that we're not necessarily thinking about the best simple solution that works, but that we're trying to show that a particular potentially complex learning controller works. And I think that's perfectly fine as long as there is a benefit that we can clearly show. So can we say the development times are better, or the implementation is improved? So I think this is something to keep in mind. And then when it comes to the specific question of PID, especially as a low-level controller, I simply don't believe that it is going away. But it might be, fully integrated in a learning chain across the different layers in the hierarchical structure of the problem. And so in a sense, it might appear as a learning controller. It might actually have learning components. You can also think about, adaptive components in a PID controller, and then it might just not be referred to that, but referred to as a learning controller. And so what we've also heard before, I think it's really a lot more about the combinations and what actually makes sense to do and leverage what we already know and integrate it with the learning. There is, of course, a little bit of a pressure that industry is supposed to do something with learning, and that can be seen critical. Sometimes it means we're not looking at the potentially best solution, but it also means that there's a lot of good innovation coming up. And I think what we also see today is that it's clear that industrial learning solutions, they need different approaches. So I think that's a very good development. So to summarize that slightly long answer, more importantly than what we call it, it's classical controller or learning controller, we should be thinking about where we apply the more complex learning methods and think about which problem class really makes sense to apply which method. So I think the big task we have.
Okay, so obviously it's not really a question whether PID is replaced by learning, but we want to look into something in between. Now, Mario, are there any architectures or theories that promise to bridge that gap between, say, deep learning and the classical approach via systems identification? What's your take on that?
Right. So honestly, I think that the divide here is whether or not you learn the parameters of a given structure. Like Melanie mentioned, you can have a PID and learn the controllers of the parameters of the PID. And if that's the case, we can already declare victory and move on and say that we've been doing learning on alone. The real issues, like Thomas mentioned, how do we put flexible elements in the loop so we can learn and move beyond given structures? And there we may have a problem. There's a very interesting paper by Eduardo Sontag that's 20 years old by now, and I think it's a little bit unappreciated. He showed that to control a nonlinear system using a recurrent neural net, you need at least 2 layers, which is a little bit surprising because everyone knows that to approximate a continuous function, you need only a single layer. I mean, that's what Sivenko tells you. So that shows that learning for control, it's not the same as just learning a smooth function. There's something else in there. So your flexible method cannot be entirely agnostic to the fact that you're trying to learn for dynamics. So recently, I've seen lots of papers. I'm getting really excited about using the framework of Koopman operators, where you use deep learning to actually learn the eigenfunctions of the Koopman operator and then the linear dynamics. And that seems to have the right flexibility because on one hand, it has deep learning. On the other hand, it's rooted in deep theory from control. I mean, it's rooted in delay coordinates and Takens embedding theorem. So it has the right blend. And I've seen some amazing results where you can actually learn to predict the behavior of chaotic systems, like the Lorentz attractor or the Duffing oscillator. So I think the message in here is, yes, we need flexible methods. No, they cannot be agnostic to the fact that we're learning dynamics. You need to find the right balance. And whatever structure or method you have, it has to be sensitive to the fact that you're modeling a dynamic system.
Okay, so that was clearly a view from the control perspective on that interface, let's say it this way. Let's have the other look. Thomas, when and how do you think deep learning will really advance system identification and control?
Yeah, that's already happening, I'd say, but way slower than I would have guessed. And if you look at other fields like computer vision and speech and so on, this is happening at a way faster pace. But it started, it for sure. And I'd say, talking about this, I'd say now is really the time to think about what comes after deep learning. So you should spend some time on that, I recommend to everyone. But if we talk about deep learning now, for system identification, where I'm active, we are starting to see encouraging results when we use more or less standard deep learning solutions to our classic benchmark data sets. So now that we have seen that has taken us a few years to play around with, and we're now starting to tailor the model. As Mario just said, we know quite a bit about dynamics that can be included into these deep learning models. And that's also something that we can take with us, and we actively do that from control into other areas, because it's not just dynamics. There are other so-called sequential models that you can learn using these. And that's still early days, but you can definitely see interesting things. Also, when it comes to using deep learning for regression problems, which is what we typically do in system ID and control, there's actually surprisingly little done. And there are some fairly fundamental questions still open. So that's also an interesting topic that we're actively looking into. Whereas for classification, we know roughly how to set it up. But again, for regression, you can join us in looking into that. There's definitely more things.
Okay, seems you all agree that it's not an either-or question, but it's the combination. Melanie, do we just need to combine blocks and tools from both fields, or is getting to that interface, to this future use of both worlds, a little more complicated than that?
I would say it's a start. And now there's many tools out there which allow people to just get started with the methods and start combining them with their controllers. And I think that's, in a sense, it's good because it gets everything going, and it also gives you a certain benefit. However, it's also clear that this is not going to get us exactly where we want to be, and you're often making compromises on the performance or on the safety side, or you may not be able to run it in reality at all. So for example, if we did sort of the Gaussian process in our model predictive controller and then ran it in an online optimization, then we wouldn't have thought about the complete problem and its structure, then we would have never been able to run that in real time. Or these safety mechanisms that we use to safeguard reinforcement learning methods. It's also very clear that if you do this, in order to analyze the performance of the reinforcement learning method, you really need to analyze it together with the safety mechanism. So here you wouldn't be losing safety, but you would clearly compromise performance. Then for other problems, of course, if you start coupling sort of two processes where you don't really understand their inner workings, it's easy to imagine that things go completely wrong. So I think at least if we start combining these tools, we really need to understand their properties and what we're actually getting as an output. But of course, ideally, and this is where the exciting research lies, we need to get rid of these boundaries and view it as one system. And here I think a little bit of it as sort of model predictive control and optimization, where we made that step and realized that we should be really considering the optimization as part of the controller. And with learning, I think this is the next step. We need to consider the learning process as part of this entire system in order to be able to do all the things that we envision, really doing online learning and closed loop, etc. And that's where we then get also all the exciting new research questions. And it's been mentioned that this is now, it's becoming sort of a new domain, community, workshops, conferences, where people now really start to dig deeper into that question of what's really special when you're learning for a dynamical system or for a control system. So I do think those are exciting times, and we can do a lot more than just combining different tools.
Okay, great. So let's take a different angle view. Carsten, are you having an inferiority complex when you talk to your machine learning colleagues? They can handle gigabyte of data, and all people in model-based control can do is 1,000 points. Any ideas why?
Oh, that's a well-taken point, I think. You know, complexity hits us all around in control, in particular in model-based control, computational complexity. But here I think you're referring to system identification. I guess that's a more question for Mario. I'm not really an expert in those things. But still, I mean, if you think of modeling next to learning prediction models or regression models or just classifying data, we are really interested in understanding the structural properties, the essential dynamics of a system, or invariants related to the plant that determine the limits of performance if you control such a system. And understanding that and learning these essential features might bring down the corresponding computational complexity that's involved in controller design. So complexity is not determined by the sheer amount of data, but by such structural information. But how to bring that in? I mean, I'd embrace machine learning techniques that permit you to do that, and to really understand the information in data for effective use in controller design. Or another side of the story maybe is give up on models completely, this end-to-end controller designs with guarantees and can we use data directly for control? Is that the way to go? And of course, there is quite some activity in this direction already again. But I wonder whether we can learn from machine learning, from the area of machine learning, how to develop data-efficient control algorithms for these complex dynamical systems, very much in the way that Melanie has been mentioning it. And also there I see a strong need to really incorporate in these direct design methods partial prior knowledge about models and merge this with data on top of that, in order to get the reduction of the complexity and increase sample efficiency. So I really strongly believe that in here, we should really aim at least from a theoretical point of view, at crisp and broadly accepted paradigm problems that might give us a boost for progress to really get the crucial insights that are required for further research. Maybe if you allow me to bring in another aspect, even if you talk about what machine learning can do for classical control, in terms of computational complexity, I mean, it's really amazing how big the problems are they can handle. And even if you think of using convex optimization for designing controllers, or if for relatively small models, you are hit by this complexity, numerical sensitivity, and all those issues. So I would be really also liking to see whether machine learning has to offer something about that. For example, the simple good old question of doing output feedback stabilization for a large scale system static output feedback stabilization. So I question whether computational tools from machine learning could come to a rescue over here. So yes, this is really hitting us and hurting us, but I think we should really get to know better what the crucial issues are.
So Thomas, sometimes we get the feeling that people think the more data, the better the paper, correct?
Sometimes I guess that is correct in terms of certain applied papers. I've written a few of those where the data is really the key aspect. But I think when it comes to understanding the technology, in terms of if we focus on deep learning for a second, then I think the data is of course important. But I think the most interesting papers are still to be written in this area, and they will not have too much data in them, or they will not have to have much data in them, which shed lights on why this actually works. So by now we know that it works on this problem. We still don't understand exactly why. So I think those papers, of course, they will come, and they will not necessarily have data in them.
So, Mario, it's obvious you still dream about this first-class flight, right?
Yes.
Why not sticking your favorite machine learning algorithm into the loop of your favorite system and create a startup selling that? Big money on the horizon and any first-class ticket for you, whether it's self-piloting or not.
Actually, that's an excellent question. I think that the Congress is going so well that Ifac is probably going to give me some venture capital. I just need $1 million or $2 million. And then I need a commitment from Carson to come and work for me. And unfortunately, I can pay him only with stock options. But Frank mentioned that there's about 1,000 people looking at this plenary. So if I could do crowdfunding, $100 each, I'm there. I also have a name for my startup. It's called Classic Control Inc. And the classic comes from classifier in the loop. So, but honestly, I think that putting a classifier in the loop, it's a good starting point, but that's not the end of it. I mean, if I can put a classifier and then deal with Carson at a very crude level, you can think of the classifier as giving you the parameter on your LPV system, and then I use Carson theory, and then I'm all set. Okay? That's just a starting. I don't think we can coach every control problem by just putting a classifier in the loop, especially if you also have to come up with a controller. So in a broader sense, one thing that we don't know yet is what do we need to learn? Do I actually need to learn to classify, or can I just go ahead and learn, say, an invariant set, a control Lyapunov function, and that will obviate the need for a classifier, okay? Having said that, I think the classifier in the loop is a really good starting theoretical point, because then you can model your system as a hybrid system with the switch surfaces given by the surfaces of the classifier, and you can start bringing theory in there and start bridging the gap between machine learning and hardcore control and get the certificates we started this panel talking about. But as a company selling just classifier in the loop, I mean, I had an idea that I want to run by you. You know, I drive an old Volkswagen bus, and I was going to put a classifier in the loop that tells me how to change gears. So maybe I can get it to 70 kilometers per hour and drive on the Autobahn. But probably the market there is a little bit limited. So honestly, I think that we're still at the stage where we're still learning what do we need to learn before we can actually stick our controller or machine learning artifact in the loop.
Okay, thanks very much, guys. Let me try to summarize the outcome of this first live plenary panel at the World Congress. So different from fields like picture classification, language translation, video games, and quite a few things more. The use of machine learning techniques and maybe KI in a little bit more general will probably not lead to quick successes in hardcore control problems, at least not when guarantees for a proper functioning need to be given. But our panelists seem to also agree that the interface between machine learning and control is certainly an area with many interesting open research questions and with significant potential. not only during this World Congress, we will hear quite a bit of advances in this direction, but also for the years to come. So with a final verdict, we will have to be patient and wait for those breakthrough advances to come, or maybe not to come. So this closes our live panel session on control and learning. Is there really a divide? Next on the agenda is a special social event. We prepared an online quiz, bringing the participants of the World Congress together. The quiz will start shortly after 3 p.m. Berlin time. We recently distributed the Zoom link with various emails. If you did not receive it, but would still like to participate, which I really highly recommend, you can do this still in the lobby by clicking on this news update button in the top right corner of your screen. There you can find a link to this quiz. So see you there in a few minutes. Thank you very much for listening to this panel discussion.